Now, in a previous video, I gave you kind of an overview of calorimetry. In this video, we're going to work one specific problem, and this is the idea of finding the heat capacity of a metal submerged in a calorimeter. Now, I don't like videos like this because they are very specialized videos and they are not broadly applicable. So these are more focusing on problems that we would see in the chemistry 1 level. Synopsis is, we have our styrofoam calorimeter filled with water, and to it we're going to add some block of material. And this material is going to heat the water up or cool it down depending on the starting temperatures. Now, for all calorimetry problems, there's one relationship that will always hold true. The heat gained or lost by our system is the opposite of the heat gained or lost by the environment. So Q sys equals negative Q environment. Now, how do we use this? We have to define our system and we have to define our environment. So in this case, we're going to define our metal as our system and our water as the environment. And since we're looking with a calorimetry experiment, we're going to have the relationship that the Q of the environment is mCp delta T. The mass of the water times the heat capacity of water times the change in temperature of the water. Well, how about the metal? Well, in a problem like this, we'd be asking like what mass of metal, or what was the temperature change of the metal, or what was the heat capacity of the metal. But in all cases, we're going to have the relationship Q of sys equals mCp delta T. But here we're going to have a little subscript m for our metal. So for this, got a handy dandy worked example. So what we want to know is, what is the heat capacity? Cp of a metal. If we have, sorry, I got to read it off the list for you here. If we have 100 grams of water, 75 gram sample, and the starting temperature of the water is 20 degrees C, the starting temperature of the metal is 100 degrees C, and they both finish at 25 degrees C when we finish. So hopefully that's popped up on the screen. You can pause the video and write that down. So how do we solve these types of problems? Well, we just need to identify all the terms we have and all the ones we're missing. So for the water, we have M over water, Cp over water, final temperature minus the initial temperature. For the metal, the mass of the metal, the Cp of the metal, and the final temperature. And we're going to do a T0 here for the metal itself. We know these are related through a negative relationship, so we get the mass of the H2O times the heat capacity of the water, T final minus T initial equals the negative, because we have a negative, mass of the metal, Cp of the metal, final temperature minus the initial temperature. Now, the assignment of the negative here is arbitrary. It doesn't matter which one we put it onto, we can always shift with a negative. The reason we need a negative here is the water is going to start out cold and it's going to get hot because of the metal. So this is a positive delta T. With the metal, it's going to start at a high temperature and it's going to cool down. And because it cools down, this gives us a negative delta T. And this negative here helps us more easily, well, basically cancels out the negative sign, guarantees we always get positive values. So we are being asked for in this problem the heat capacity of the metal. So all we have to do is take this full relationship and solve for Cp of the metal. So we have our mass of water, heat capacity of the water, T final minus T initial, all over the mass of the metal, T final minus T initial of the metal, negative. We're given 100 grams of water, 75 grams of metal. The heat capacity of the water here is 4.181. The initial temperature of the water, double check this just to be sure, it's 20 degrees. Final temperature is 25. The metal starts at 100 and it finishes at 25. Now, in all cases, the final temperature of the water and the metal are going to be the same because we're going to set the stipulation here that they are at thermal equilibrium. So at thermal equilibrium, both your system and your environment have to be at the same temperature. And for those of you playing at home, when we work this all out, the Cp of the metal ends up being 0.115 unit here, joules, grams, degrees C. So if you're ever given a problem where you're asked to find the heat capacity or something related involving the heat capacity of a metal in water or some material in water, basically you said that you have two materials, there's no reaction. How do you find the missing variable? These are your two ways to describe the system and the environment. Environment, mCp delta T, your system, ncp delta T. Now you can be asked to find anything, final temperatures, initial temperatures, masses, and CPs. But you're basically going to end up with this formula when you finish. And you need to identify the variable you're looking for and solve for it.